Welcome everyone to our first part of Lecture 5, Lecture 5A. In this lecture, we are going to be looking at the introduction to character tables. Now, with Lecture 5 as a whole, this is going to represent a little bit more complex material than we've had previous. It's probably some of the most complex material that we've had in the course. So make sure you stay up with the content. If you have any questions, just write them down. And you are always free to either contact me directly through email, in person in my office, or you can always bring questions to our Panda sessions on Thursdays. So what happens when we have bigger molecules? What happens to a molecular orbital diagram if we have something bigger than a diatomic molecule? We've looked at homodiatomics, we've looked at heterodiatomics. Now, what if we have something that is triatomic or tetratomic, just 4 atoms, 5 atoms, 6 atoms? What do we do when we have these and we need to make an MO diagram? Just some very simple examples as far as molecules: H2O, ammonia, CH4, can create very complex molecular orbital diagrams when you're having to look at how all of those atomic orbitals interact to form molecular orbitals. So, as you said, this is a much more difficult problem than a simple diatomic, and we need to involve the symmetry of the molecule. But before we do that, we need to learn about character tables, because they really tell us how the symmetry of the molecules and the symmetry of the various atomic orbitals come together and interact. So let's look at character tables. Well, what is a character table? A character table represents the characters, which are traces of matrices, of the irreducible representations of a group under its symmetry operations. I know that sounds a bit of a word salad. Just bear with me. We'll get through these definitions, and then hopefully it'll start to make sense here in just a little bit. So what else does a character table do? It gives you information to help interpret the symmetry of molecular orbitals, any vibrational modes, and electronic states in the molecules. And we'll take a look at vibrational modes and electronic states next week when we're looking at applications of how we use these character tables outside of just molecular orbitals. And then each symmetry operation that we have is represented by a class of operations. And these are elements that are conjugate to each other, and thus they have the same effect on the molecule. So let's look at the structure of a character table. A typical character table includes symmetry operations. These are represented as column headers. So here we see that we have E, which is an identity operator. Here we have a rotation operator C. Don't pay any attention to the 2 just yet. We'll look at that in a little bit. We have a sigma, which is a reflection operation. Here we have another reflection operation. A couple of operators that we don't show in this particular character table is an I, which is a center of inversion, and an improper rotation. And we're going to look at all these various operations in detail in just a little bit. Other things that we see in a character table are the irreducible representations, and these are listed as rows, and they have labels such as A1, A2, B1, B2, E, T, T2G, EU, or whatever. It just depends on what the symmetry is. And these describe how a molecule's symmetry, or how its symmetry elements act on the various modes within that molecule. And then we have the characters. Okay, and here are our characters in here. So here, this was our A1, A2, B1. These are our irreducible representations. And there are characters here. These show the trace of the matrix, which is the sum of a diagonal. And it tells us the trace of that matrix for each symmetry operation within each irreducible representation. Again, this sounds very complex. We're going to go through some examples to see how all this works out. So we did see a lot of symbols there in the character tables. We want to take a look to see what they all mean. So in that first row of the character tables, so these are your column headers. When you see an E, every molecule, every character table will have an E, because this is an identity operation, and that leaves the molecule unchanged. In other words, it's a required part of the math of the character table. So what happens if you just leave the molecule alone? And that becomes its identity. That is its identity. So every molecule has an identity, and so that's why every molecule has an identity operation. Some things have a rotation operation, that's C, and the N represents just a number. It's usually 2, 3, 4, 5, or 6. And it means that you can take a full rotation. Sometimes you'll see this as 2 pi if they use radians, or 360 degrees if they use degrees. We see that down here. But you have a full turn divided by n. So this is the number of turns in one circle on the main axis that doesn't change the look of the molecule. So if you have like a square, if you can imagine just the shape of a square, that would have a C4 axis that runs down through the center of the square, because you could turn it 90 degrees and the square looks exactly the same. And so 4 would be 360 divided by 4, so 90, so 90 degrees. So it would have a C4 axis. It would also have a C2 axis, that would be 180 degrees. And so you can turn the square 180 degrees and it will look exactly the same. A CN prime, and all that is another rotational axis that is perpendicular to the main axis. And you may have a CN double prime, and this is another axis perpendicular. It's perpendicular to both the CN prime and the main axis without changing the structure. So if you had if you can imagine an XYZ coordinate system, your Z in our definitions is always going to be your main axis, the main axis of the molecule. And so an X might be the CN prime, and then a Y would be a CN double prime. So the X is perpendicular to the Z, so you could call it a CN prime, and the Y is perpendicular to both the Z and the X, and so it would be a CN double prime. We have our sigma reflection planes. We don't see the sigma prime too often. We see sigma V, and that just means that we have a reflection plane that is parallel to the highest C axis that we have. If you have a second one of these, so if you have a second sigma V, you would call that a sigma prime V. Okay. You can have a sigma H, which is H is for horizontal, and so this would be a reflection plane that is horizontal compared to the highest axis, the highest C axis that you have on there. And you can have a sigma D, which is a little bit different as well. That's a diagonal. We'll take a look at examples there. We have an I, which is an inversion of the molecule through a center. And what that means is you can reflect atoms through the center of the molecule. And when you reflect everything through the center of the molecule, or invert it through the center of the molecule, you still get your exact same molecule back. SN is a complex operation, so that involves a rotation of a certain number of degrees and then a reflection perpendicular to that rotation, and you end up with the exact same molecule. And I'll let you take a look at those other definitions there. The one that's strangest here is if you have a rotation, so like a C2, you may also have a C4 axis. And so kind of like the square that we mentioned. So we would call a C2 is the same as a C4 2. So it'd be C4 done twice. That becomes a C2. And anytime you see a number in front of one of these operations, it just means that there's more than one of those similar operations at different places in the molecule. So if we look in the first column where we have irreducible representation designations, you might see an A. That means it's singly degenerate, so you'll just have one molecular orbital there. It's symmetric with respect to the rotation of the principal axis. If you have a B, also singly degenerate, it's anti-symmetric with respect to the rotation axis. What this usually means is it's something that changes sign or changes phase for an orbital. If you have an E symbol, that means that you have doubly degenerate orbitals, and so you're always going to have two molecular orbitals there at the exact same energy. Or if you have a T, it means that it's triply degenerate, and so you would actually have three orbitals at the exact same energy. If you see a subscript 1 there, like an A1 or an A2, A1 means it's symmetric with respect to a C axis. And if you have C a subscript 2, it's anti-symmetric with respect to a C axis. The ones that always confuse people a lot of times are the G and the U. A G just means it's symmetric with respect to an inversion center. It stands for Gerade. And subscript U, ungerade, means it's antisymmetric with respect to an inversion center. So the only time you see G and U in your irreducible representations is if you have an inversion center. If you see a prime, it means it's symmetric to a horizontal mirror plane. And if you see a double prime, it means it's antisymmetric with respect to a horizontal mirror plane. Some of the other characters in the table, so when you see just ones, twos, zeros, or something, if you see it's positive, that means that that function is symmetric and remains unchanged under the operation. If it's negative, it means that the function is antisymmetric, so you change sign, or you can think of it as changing phase under that operation. If you have a zero, the function changes in a way that's very complex. This happens quite frequently in E or T representations. You may have various functions canceling out during the operation. If it's greater than 1, you can see this also with E and T representations. That means that you have degenerate representations, and these represent the total change within. So you may have two orbitals that have a 1 change, and so that would indicate as a 2. So again, you're just some key elements here, your irreducible representations. They show how each molecular property, such as vibrations or orbitals, transform under the group symmetry operations. For instance, an A1 usually represents a symmetric stretch. It is invariant under all operations, so it never changes. B2 might represent asymmetric motions due to changing signs. Our characters, again, these values within each row, they give a quick view of the effect that each symmetry operation has on the function, the mode, or an orbital present. We'll see that with orbitals. We'll also see it with functions for spectra. Places we can use these character tables. Next week, we'll take a look at spectroscopy, look at molecular vibrations, look at infrared, Raman spectroscopy, active or inactive. Molecular orbital theory, which is what we're going to focus on in this lecture. We'll take a look at orbital symmetries, what orbitals might overlap to form bonding interactions or anti-bonding interactions or non-bonding interactions. And we have vibrational analysis. So again, you can look at molecules, infrared or Raman spectrum, and figure out which bond is vibrating at certain frequencies.